Weight optimization through differential evolution algorithm in neural network-based ensemble approach. Abstract. In recent years, with the advent of computational intelligence, machine learning has remained an extremely popular area for research. Till now, in this field, many machine learning models are available for prediction. So, rather than implementing new machine learning method, we should go for ensembles of these models for getting better results. The ensemble learning to represent the most innovative strategy in the field of machine learning. It provides better predictions than ordinary machine learning approaches and provides better accuracy. Generally, in machine learning, only one learner is used for the training and prediction, whereas ensemble learning methods to build a number of learners and then aggregate their results to obtain a more precise prediction. In this work, neural network ensemble is used and the weights for predictions are optimized using differential evolution algorithm to obtain a more precise final prediction. Comparison between NN-ensemble and other ensemble approaches is performed on various evaluation measures and NN-ensemble outperforms with accuracy 91.82%. Keywords: machine learning, neural network, differential evolution, algorithm, ensemble. Introduction. Machine learning represents an application of artificial intelligence, AI, that provides frameworks the capacity to consequently take on and enhance as a matter of fact without being expressly customized. An ensemble is a group of items viewed as a whole rather than individually. Ensemble learning utilizes a technique that applied to provide training to multiple learners and aggregate their outcomes, considering them as a committee of decision makers. The key idea behind it is the decisions of the committee, with single predictions aggregated suitably, ought to have more acceptable overall accuracy, on average, as in contrast to any committee member. The ensemble members might be predicting real values, labels for class, posterior probabilities, clustering, rankings, or any quantity. So that their predictions can be integrated with distinct techniques, including voting, averaging, and probabilistic methods. Predictions from machine learning algorithms play a vital role in modern humans' life. As a user of technology, we complete certain tasks that desired to make a decision or classify something, like in the medical field, research and development, also in our day-to-day life and in any data analysis task. There are several machine learning algorithms like the random forest, k-nearest neighbor, decision tree, support vector machine, etc. Pantala et al. Presented an ensemble technique with the weighted average strategy to combine machine learning models to obtain a more precise prediction. In weighted average strategy, weights are assigned manually to achieve precise results from ensemble model. Hence, it is a limitation of traditional ensemble approaches. Manual assignment of weights increases the probability of not getting the increased accuracy of ensemble model. Instead of assigning weights manually, there may be some method or algorithm to find these results. In the literature, there are many methods for finding weights for ensemble model, like IJERT, for finding weights for fusion used for grid search, and IDNA-KACCL also used for the same purpose. 3. Liu, Zhang et al. Proposed a method that measures the distance of incorrect classifying data values, and for clustering, it used affinity propagation algorithm. 4. Many more methods with fuzzy logic are used in literature to aggregate classifiers, like multiple kernel learning for better prediction. 5, 6, 7. Samples having high fuzziness get higher incorrect classification cases. To get rid of divide and conquer method is proposed. 8. For getting better performance through machine learning models, their ensembles approaches should be refined. In bioinformatics for protein structure prediction, Rana et al. Showed that random forest gives a more precise prediction for classification and regression data. 9, 10. Then neural network ensemble 11 approach is proposed by Rail and Rana on regression dataset, and more promising results are gained. They compare classical ensemble approaches with neural network-based ensemble approach and found that Ensemble 12 outperform. But there was not any scheme to optimize weights to get better predictions. So, in our proposed work, we are also working on neural network-based ensemble approach for protein structure prediction using regression dataset. Over here, weight optimization is done through nature-inspired algorithm, NIA, which is differential evolution, algorithm. The paper would be structured as, in material and models, the description of dataset and models is provided. In methodology and implementation, differential evolution algorithm and proposed work are discussed. Then experimental results and k-fold cross-validation for proposed work is explained and complete work is enclosed in conclusion. 2. Material and models. A. Data with its description. Proteins are the core component of our life. Proteins provide the foundation of structures such as skin, hair, and tendon, and they are the primary cause for catalyzing and synchronizing biochemical reactions, transporting molecules. 13. Regression data. 14 is used with the proposed approach, for protein structure prediction. The physicochemical properties of a protein structure are used to determine the quality of the protein structure. Therefore, these properties are utilized to identify native or native-like structure from various predicted structures. In this work, the machine learning regression models are experimented with 6 physicochemical properties to predict the root mean square deviation, RMSD, of the protein structure. This prediction works in the absence of its true native state, and each protein structure ranges from 0A to 5A RMSD space. Physicochemical properties explored in the paper are as described, with each attribute in table I. RMSD value is predicted and equated with known protein structure 9. In the table 2, a sample of data of 5 instances is shown from the specified data set. For regression purpose, the value of RMSD is considered as continuous. B. Machine learning models. This section explores the entire machine learning model description with configuration and specifications, and these are depicted in Table 3. 3. Methodology and implementation. A. Differential evolution, algorithm. Differential evolution, algorithm is an optimization technique with stochastic nature. It is an evolutionary algorithm, EA, with faster and simpler evaluation process. It was invented by Storn and Price 17. The steps involved in is shown as a flowchart in Fig 1. The procedural illustration is provided in Algorithm 1. In a solution is finding by potential solutions, individuals. The search space is a d-dimensional space defined as I equals 1, 2, Sn, where Sn is the population, number of individuals. The algorithm employs the operators, namely mutation, crossover, and selection. Initially, to find a trial vector, mutation operator is utilized for each individual of the present population. Then, using crossover operator, parent vector and trail vector are generated, and after this generated offspring is compared with the parent. In selection operator, 2 functions are there. First, mutation operation with a selected individual is used to generate a trial vector. Second, for the next generation select the best fitness values between parent and offspring. At the end return individual with the best fitness as solution 18. In our work, we are using DA for finding optimized weights so that we can achieve improved results from the complete ensemble model. For this reason, we have considered our objective function as follows. Equals, asterisk. 1. Where, Y represents the actual RMSD and She represents the predicted value of the top 3 models. WI is the optimized weights for each model's prediction in top 3 models. B. Methodology. The proposed approach is shown as a step-down flow diagram in Fig 2. It is organized in 4 parts. 1. Data splitting. 2. Train and test base models, selection. 3. Weight learning through the algorithm. 4. Train and test neural network. Dataset is loaded and 75% of the dataset is the training data, set 1, and rest of the dataset, set 2, is used to test the NN-ensemble model. So, the training data is expressed as set 1 and testing data is expressed as set 2. In the phase 2, after getting data from phase I, dataset, set 1, is further partitioned into a ratio of 2:1. This specific data splitting is used to fit more efficient ensemble model without compromising the testing data. Further, base models are trained on 50% of the whole dataset and tested on 25% of the dataset. After obtaining prediction results, top 3 base models are selected based on accuracy parameter. In the phase 3, top 3 models prediction and corresponding target RMSD are used to form a dataset, and weight learning is done through the algorithm 1. It will tune the parameters and determine the optimized weights to form new training and testing dataset for complete ensemble model. In the phase 4, train the neural network by establishing the relationship between top 3 models' actual predicted values with optimized weights. This special combined data is used to improve the performance of final ensemble model. The set 2 dataset is used in the same way as training to perform testing of the final ensemble model. See model evaluation parameters. The prediction results are compared and priority is given to the models by considering their respective accuracy. Accepted error. The acceptable error range ranges from 0,1. It defines acceptable error range between predicted and actual value. Accuracy. Accuracy is defined in EQ2 for the regression data model, where Y is predicted target and Y is actual target. Total number of instances is denoted by N. Correlation. R correlation, R, for actual and predicted value is measured as Pearson correlation, which is defined as where X is actual and Y is predicted. The total number of instances is denoted by N. Value of R ranges from -1 to 1. R2 represents the variance proportion of the dependent variable explained by the regression model. RMSE, root mean square error, RMSE, is used to measure error rate of regression data model. It is measured as where, as is used for actual and P is used for predicted value of target, and N represents the total number of instances. D. Implementation. The proposed procedure is followed as shown in algorithm 2. The procedure is followed by 4 phases to process data and evaluates results from complete ensemble model. 4 experimental results. A. Results and discussions. This section provides experimental results obtained from base models and ensemble models are presented in tabular format. Table 4 shows the base model's prediction results in terms of evaluation parameters, i.e., accuracy, R, R2, and RMSE on the test data set, set 1, 2. Top 3 models are selected on the basis of accuracy for further processing with an ensemble model as expressed in the algorithm. These top models are highlighted that are more accurate than other models, having least RMSE, highest accuracy, correlation and R2. The according to Pearson correlation formula, if the attributes are significantly correlated with each other, then correlation will be high. Over here, correlation is compared between actual and prediction values of these models, and according to that accuracy is measured. According to results, top 3 selected models are Random Forest, Cubist, and SCBust are used for finding optimized weights according to the objective function definition with the algorithm. Top 3 models prediction sample is depicted in table V. The algorithm uses actual and predicted values of the top 3 models as input and returns output. It provides the most appropriate combination of weights or optimized weight for better results. After that, we will apply these predictions and weight combination to ensemble model as training data and testing dataset set 2. It is also using these weight combinations, and on this dataset, complete neural network ensemble model is tested. Complete ensemble is evaluated on actual and predicted values. Results achieved from neural network ensemble are also compared with classical ensemble models. Table 6 show the prediction results in terms of accuracy obtained from selected models, its classical ensemble technique and neural network ensemble technique. Experimental results show that neural network ensemble outperforms among all these ensembles. It is because NN-ensemble training establishes the more accurate relationship between actual and predicted classes. Because of weight optimization, neural network performance increases and provides the more efficient performance as compared to other ensembles. B. Validation. Validation, i.e., proving the validity or accuracy of anything, is a technique that is properly used in machine learning to measure the robustness of the final model. For this reason, we have performed k-fold cross-validation 8 with the final ensemble model. Over here, we have considered k-size as 10-fold, i.e. the models are trained and tested each time with random data samples of the same size. This test found that in each fold ensemble perform in a uniform way. So, these results testify to that NN-ensemble outperforms for regression dataset. The validation results for all ensemble models are presented in Table 7 with 10 iterations of folds. Fig 3 shows that ensemble of neural network performs more efficiently than classical ensemble approach. It demonstrates that due to optimization of weights through the algorithm, neural network-based ensemble approach performs in a more accurate way. See conclusion. In this work, Differential Evolution, DE, algorithm is applied for optimizing prediction from top 3 base models to improve the results of neural network-based ensemble approach. Initially, 10 models are trained and tested and top 3 are selected based on accuracy. Next, these predictions are optimized through DE to improve the performance of the final ensemble model. Data partitioning is done in a specific way to achieve the extremely efficient model. The neural network is used to ensemble the models because of its generic nature. The experimented results have been evaluated through data tables, verified through k-fold cross-validation method. The obtained results clearly show we can improve ensemble model results by optimizing parameters. Model evaluation is done through evaluation parameters like R, R2, RMSE and accuracy, and compared other ensemble approaches. It is expected by using more physical and chemical properties may result in improved accuracy and can decrease computing time. Other nature-inspired algorithms can also be used to enhance the performance of ensemble models. This idea would represent an efficient approach for protein structure identification. Additionally, this work can be prolonged in the prediction of template modeling, TM score, and global distance test, GDTTS score. So, at the last, we can say that instead of making new machine learning models, we can improve ensemble results through an effective optimization scheme.